Okay, I'm recording now. Okay, so we haven't talked about alkene reactions yet, and there are more of them. There are 5 reactions we'll go over, and they're much more interesting than the reactions for alkanes. Now, alkane reactions, there are 2. There's a combustion reaction where you add oxygen, excess oxygen, and you'll end up with carbon dioxide and water. If you restrict the amount of oxygen, you'll get either carbon monoxide or solid burning carbon. The other reaction for alkanes is adding Cl2. You'll end up with a chlorinated hydrocarbon. All right, alkenes, however, are very, very reactive compared to alkanes. It has to do with the double bond, the extra bond in that double bond adds a lot of instability to that bond, making it susceptible to different types of reactions. Now, the reactions form, reactions always form you had me for 305, I would stress this through the whole semester. Reactions only occur if we go from unstable to stable. It's not going to happen if something's stable and wants to become something unstable. Nature doesn't like that, and it doesn't happen. The only way that can happen is that we have to add energy. Okay, so having said that, that means that this guy is more unstable than this guy. And it's because of the double bond, the placement of those electrons in that double bond. In fact, the double bond is made up of 2 bonds. One's called a sigma, the other's called a pi bond. Pi bond is the one that's unstable. Okay, so we're going to be...
Professor, why is a double bond more unstable than, say, like a single bond?
It has to do with the potential energy of the electrons in the bond. Higher potential energy means it's more unstable than low potential energy.
Okay. And then the other reason was you said the placement of the lone pairs?
The placement of, yeah, it's the it's the pi bond part of the double bond that's really unstable. And it has to do with how much potential energy is in that bond. It's really high.
Okay, got it.
So by forming a single sigma bond, it's much more stable. So unstable wants to become more stable, kind of like life. We don't want instability in our life. We want something stable. So what are we going to do? We want to go in that direction. We don't want to go into the unstable direction. So now there are a number of different types of classes of reactions. In our book, we're going over sections 4, 5, and 6. And at the end of the chapter, on page 427, they summarize the reactions nicely as well. So that would be a good page to copy and really become comfortable with that page, as well as our diagrams I put together like this. And we'll be going over these lots. Okay, so whenever we add something to a double bond, that is called an addition reaction. It makes sense. We're adding something to the double bond. Okay, in this case, it's a chemical AB. And we're going to look at a lot of different versions of what I mean by AB. It could be H and Cl. It could be Cl and Cl. It could be H2O. There's a number of chemicals that are able to add across the double bond. And then the subsequent structures you get once the reaction is complete is what makes this real interesting, particularly compared to alkanes. Alkanes are, ludicrously simple. Okay. All right. So this is where we are. There are 5 reactions, and the one that isn't in here is called combustion. So those are the 5 reactions. If we add H2 across a double bond, we're going to get an alkane. If we add Cl2 with a double bond, we're going to get it's called a haloalkane. In other words, Cl on a alkane in some position. It could be in the middle, it could be on the end. If we add water plus an acid, sulfuric acid, as a catalyst to that reaction, we'll end up with an alcohol. If we add, and usually it's hydrochloric acid again, we add hydrochloric acid across the alkane, we're going to end up with a haloalkane again. In other words, that Cl is going to be on the carbon backbone somewhere on the end or in the middle. So those are the 5 reactions for alkenes. Now, there's also some reactions for the aromatic alkenes, which those aren't very few because the aromatics are extremely stable. So it's hard to get a reaction going with them. Okay, so the first addition reaction I want to talk about is called halogenation. Now, this is the way they used to make pesticides a while ago. Back in the 30s and 40s, this is how they used to make DDT. This is toxic. There's a whole bunch of pesticides that are horrible for the environment, particularly if you're a bird, horrible for the environment. This is why they outlawed DDT, mainly because of eagle eggs were too soft and they didn't hatch, but it affected all avian eggs. So halogenation. Okay. What we're going to do is we're going to add Br and Br across that double bond. Okay, so we're going to be adding this across the double bond. And what's going to happen is so that unstable pi bond is going to become a single bond, much more stable. So we go pi bond, unstable, boom, forms a new sigma bond. Now we could do that with chlorine just as easily. So that's a halogenation reaction. So let me give you an example.
Do we need to remember the difference between a sigma bond and a pi bond? Or should we just kind of have that in the back of our minds?
Back of your mind.
Okay.
But do remember, though, that of the 2 bonds on a double bond, they're not equal. One is more unstable than the other, and the unstable one wants to become more stable. The sigma bond part of the double bond is fine. It's that pi bond that needs to be made more stable. And that's what comes up here. So that's the pi bond there. This would be the sigma. That's the pi. So the pi goes from pi to sigma. Stable, stable, stable. So if we took something like that, propene. Now you can write this as 1 propene or just propene, because there's no way to write it any other way. So organic chemists and biochemists being lazy, they just say, oh, it's propene, because 1 propene, doesn't matter which way you number it, it's always 1 propene. Okay, so propene plus chlorine gas gives us so that would be 1, 2, dichloro. Oops. Um, okay. 1,2-dichloro-propane. So we go from propene plus Cl2. You could write this like this also. You could say plus Cl2 or put the Cl2 above the arrow. Either is fine, whatever you're most comfortable with. Most people put it over the arrow. Now, whenever you do reactions, I'm looking for structures. If there's a mix of structures, the most stable one, I'm going to talk about that quite a bit in this unit. And name the structures, both reactants and products. Now, because there are 3 parts, well, sometimes you don't have a mix. I guess there's 2.5 parts to every reaction. Main thing are structures, and under structures, we need that includes conditions. Now, there weren't any conditions in this particular reaction, but sometimes there are. For example, when we add water to a double bond, it has to be a sulfuric acid present as well. That would be a condition. Or heat. In the case of heat, sometimes it's at a specific temperature. We're going to end up with heat in 2 ranges, 140 and 180. So all that would be part of the conditions. All right, so that's how
Are you saying like when we're showing our work, this is what you're looking for on our paper?
Yeah.
Or when we go to do this? Okay, so what does a mix of structures mean?
we're going to get to that in a minute. What
Okay,
happens is the for example, we add HCl to this double bond. It's going to add an H and a Cl, but it's also going to add the flip of that, a Cl and an H. That's why you end up with a mix.
okay. And then what is the purpose of writing Cl2 again over an arrow? Or is that below it? Is that not Cl2?
No, it's equivalent. So either way, whatever way you like,
Oh, okay, okay.
you'll see it frequently in textbooks. They introduce it as saying plus Cl2, and after a while, they don't do that anymore. They just put it over the arrow.
Okay, got it.
Whatever way you're comfortable with is fine with me. Okay, so we're going to run into a mix in a minute here, but when we have a homogeneous additive, no mix. When we have a heterogeneous additive, we have a mix. So I think this would be a homogeneous example. A hetero additive would be like HCl or H2O. Those would be examples of heterogeneous. And there will be then from these a mix. Okay, so the first one we did is a good example of a homogeneous additive. Another one would be like H2, hydrogen gas. All right, so we're going to get to heterogeneic ones in a minute. For now, we've done the first one, Cl2, homogeneous, additive, hence there's no mix. Okay, when we add H2, another homogeneous additive, it has to be done in presence of a catalyst, a metal catalyst. Usually it's platinum. But it could be nickel or palladium or something like that. But usually it's platinum. In fact, I've never seen anything but platinum. Now, this is a very, let me do an example reaction for you for this too. Let's look at propane again. Okay, all right. So we're going to end up with propane. Because the H's are going to
Is PT an element or is it an abbreviation for something?
it's an element. Yeah.
Okay.
It,
And what was the other two? It was PT, nickel, and what else?
PD. Just remember PT. That's all you have to remember.
Okay.
But basically, it's kind of complicated the way a metal catalyst works. It has to. There's a surface phenomenon, and it's kind of a pain. Just remember, you need a catalyst. Otherwise, it won't work. It works, but it's extremely slow. It's almost to the point of not really working. But if you throw a
Right,
catalyst,
because the catalyst is lowers the activation energy, right? So it makes it more likely to occur.
yep, exactly. So lowering the activation energy speeds the reaction kinetics. Because the activation energy is directly related. Let's see, the height of the activation energy is indirectly related to the speed of the reaction. So the higher the activation energy, slower the reaction. You're absolutely right. And you did well remembering that from 305. Very good. Okay. My phone needs charging. Okay. So what will happen here is this goes there, this goes there, so you end up with it's the same process, only we had to have a catalyst to do it as Cl2. So we have two homogeneous additives, Cl2 and H2.
And just to, sorry, I know I I keep butting in, but just to be clear, the other bonds on the C's, we can assume they already had H's because of your line drawings. So they're not just like an empty bond. They actually have an H there. It's just not shown.
Right. Remember, when you do a line drawing, there's carbons beginning and the end, and whenever there's a kink, and you have to fill in H's. So there are already existing two hydrogens there. We're just adding another one to the end and to the middle.
Okay. Okay, makes sense. Got it.
Okay. Now, whenever we get into a mix, there's something that a guy named Markovnikov came up with. And he has a rule. When we add a heterogeneic additive to an alkene, the H goes on one of the carbons and the X, whatever that is, goes on the other carbon. And then statistically, it's mixed. Now, how do you know which is more stable? Okay. Basically, there are two reasons for stability in these reactions. One is getting really high. Turn my pen. One is this Markovnikov rule. The other is symmetry. Okay, so we have this rule, plus we have symmetry. And this is regarding mixes. I'll show you what I mean by symmetry in a minute. Okay. So his rule is carbon with the most hydrogens is more stable than the carbon with the less amount of hydrogens. So let's count. We have 2, 1, 3, 3, 2, 3. So on the left, we have 6. On the right, we have 8. So which is more stable? 6 versus 8. 8 is more stable. So that would be the one that's more stable. And that's all this is. Okay, more hydrogens, more stable. And then the other is a symmetry argument. Sometimes you can't use a Markovnikov rule because various reasons, but you can usually use symmetry. So between the two, circle the one that's most stable. What that means is you'll get like a 40-60 split. You'll still get the unstable ones, but just not as many as the stable ones. Okay? All right. So now we have a heterogeneic additive, HCl. So we're going to add that heterogeneic additive across the double bond. Same thing again. We get this bond goes there, this bond goes there. So we end up with okay, statistically, that happens half the time. The other half the time, it's switched. Oops. Here we go. This. So we end up with All right, so what that means is, let me give you an example. Let's just do good old propene again. That's a mix. Now, does everyone see where I got the mix from? So statistically, the HCl is going to flop across that double bond in either an HCl or a ClH version. Totally random. Totally random. And all reactions, I don't know if you talked about this in 305, actually are like this, where you form the activated complex at the top of the activation energy curve, and then you end up either going to the product side or the reactant side. Okay, so when we add HCl across that double bond over here, it's going to form 50% of the time the H is going to be on the top. 50% of the time it's going to be on the bottom. But when all said and done is, we're going to end up with a mixture. And the mixture is not going to be equal. It's not going to be 50-50. One is more stable than the other one. Which one is it, left or right?
Is it right?
To the right. It should be recording, by the way. Some of you asked about recording. I'm going to stop this for 2 seconds. Yeah, see, it's recording. Top left. Okay, well, let's apply the Markovnikov rule first. How many hydrogens? I'm sorry, what?
I'm a little confused about the structures on the second one. So for the first, you only have 2 carbons, but on the second one, wouldn't there be 3 carbons?
There are 3 carbons on the left. 1, 2, 3. Is that which one you're talking about, or the top one?
Right. And so is that modeling that top one? Because then I don't understand where you're getting a third carbon.
We're starting with 3 carbons.
I only see 2 on top.
On top, okay. They always, that's why I like to give you an example. They're just talking about the reaction site. The reaction site.
Oh, okay.
And you can
So
have
that
carbon, carbon there, carbon.
got it. They're just kind of like zooming in.
Yeah,
And
exactly.
then that's okay, got it.
Okay, so as an example, we have 3 carbons, 3 carbon propene, throw some HCl in the reaction, we're going to end up with 2 products. Are we okay now? Still got the 3?
Yeah, all good, all good.
Okay, cool. All right, now the mix. Okay, so let's look at Markovnikov's rule. How many hydrogens are here on the left here?
Would it be 6?
Well, it'd be 3 here and 3 here. Is that what you mean by 6? There's also 1 here. Remember, carbon has 4 bonds. So we have carbon, carbon bond, and then 3 hydrogens. Carbon, carbon bond, 3 hydrogens on the right. Then we have a carbon, 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 chlorine, carbon, hydrogen bond in the middle here. So that's 7 hydrogens. Everyone see where I got the 7?
Yeah, I do.
Okay. Now, you have to be able to do that because Markovnikov's rule talks about hydrogens. So you have to be able to figure out how many hydrogens are in the sky. All right, so let's look at the one on the right. And we have 3 here, 2 here, and 2 here. Right? So the ones we're going to focus on are the terminal ends. So we have, no, I put 7 down. I'm focusing on the terminal ends here. Okay, so what would Markovnikov say about this? Left or right, more stable?
The right, correct?
What is the Markovnikov rule talk about?
The carbons that are bonded to the most hydrogen, are the most stable.
Yes, most hydrogens. Right?
So since the one on the right has 2 and the one on the left has 1, it would be the one on the right.
So which is more, 6 or 5?
Oh, I was counting. I thought I was just supposed to be looking at the ones attached to the chlorine, not the entire structure in general. Okay. So then it would be the one on the left.
Yeah, so
Wait, so you're saying, what's it called? So the structure with the most hydrogens is most stable. That's what you're saying?
on the terminal ends, yes.
On the terminal ends. Okay,
So that would be
so
terminal.
if the two, say you had 2 structures and one had like 3 and 3, but like 7 total hydrogens, and then one had like 4 and 4, but less than, okay, wait, that doesn't make sense. Okay, what if the one with the most hydrogens on the terminal ends, what if it has less hydrogens in total than the other one? Would that still be more stable even though overall it has less hydrogens?
Yeah. Yeah.
Okay.
Now, so Markov. I keep writing an R instead of an A. More.
Why is it just terminal ends? Why aren't you counting the entire structure?
Yeah, I had the same question too. Because the
Good.
first structure would have more overall, but it has just
No, they're going to have this. If overall, they're going to have the same number of hydrogens. See, we have on the right, we have 2, 2, and 3. That's 7. On the left, we have 3, 3, and 1. 7. So the number of hydrogens are going to be the same. Question is, we only look at the terminal ends. So they both have 7 hydrogens. But the one on the left has more terminal hydrogens than the one on the right. Okay? 3 and 3 versus 3 and 2.
Can we do another example of this?
Yes. Let me do one more. I need not finished with this yet. Okay, so as far as the Markovnikov rule goes, the left one has more terminal excuse me, hydrogens than the one on the right, hence it's more stable. Okay, let's look at the symmetry rule. Okay, which is more symmetrical, left or right?
The left one.
Yeah, the one on the right is lopsided. The one in the middle is symmetrical. Nature likes symmetry. So for two reasons, that one needs to be circled as the more stable one. Okay, all right. Let me give you another example. So symmetry is important. Markovnikov rule is also important. So between the two of them, should be able to figure out which is more stable when we have a mix. So heterogeneity additions, usually you have a mix. If you have a mix, then you have to figure out which is more stable. See how different this class is in 305? It's really different. Okay, so let's come up with another example. Of course, then we need to name this too. This is going to be so 2-chloropropane, 1-chloropropane. All right, so is everyone okay with this so far? I'm going to do some more examples. So, but just as far as one, we add the HCl across the double bond. We come up with the two structures in the mix. We name the two structures and we circle the one that's most stable using Markovnikov's rule and the symmetry rule. Okay, so let's do another example. All right, so the HCl now, going to add there. And then when we flip the HCl to ClH, it's going to add there as well. That's where the mix comes in. So this was where the double bond was, right across there. And we're going to be naming from the right to the left. So this is carbon 2 and 3, 2 and 3. Okay, did everyone see how I ended up with that mix?
Yes.
All right, now, which is more stable? The one on the left or the one on the right?
The left.
Why?
Because it's more symmetrical.
Yep. And you look at, that's right. So let's look at symmetry is left. And then what about Markovnikov's rule?
Would they be equal in terms of Markovnikov's rule?
Yep.
So
So-
then if they're equal, you base it off of their symmetry.
Exactly. That's why I'm telling you about symmetry, because Markovnikov's rule works sometimes, but not always. In this case, it doesn't work at all because the N terminals are equal. But symmetry, definitely the one on the left is more symmetrical than the one on the right. So we have to name this one. So it's five carbon backbone. And on carbon 2 is where the double bond starts, carbon 2 to carbon 3. Now, so if we named it from left to right, it'd be 3 pentene. So 2 pentene is lower than 3 pentene. Okay, this here is going to be 3 pentane. This will be 2 pentane. That's supposed to be a null set. Okay,
So in this case, both of the structures have the same number of hydrogens on the terminal ends, and that's why Markovnikov's rule is not applied, and we're only looking at the symmetry, right?
yeah.
Okay.
Yeah.
Just to clarify, the difference between the Markovnikov's rule and symmetry is that Markovnikov's is just looking at the terminal ends and symmetry is looking at the entire molecule.
Yes.
Okay.
Now, what's nice about symmetry is, I don't know if you talked about this in your 305 class, when you look at your orbitals with electrons, remember when you filled them, if you had like p electrons, you filled each one once, and then you went back and started pairing them up. And the reason why you do that is for symmetry reasons, because the symmetrical 3 orbitals have 1 electron apiece, and they're more stable than if you start pairing up the one on the left, and then the other one of the others is empty. Again, nature likes symmetry. And some of it might be. Okay. So let's talk about another heterogeneous additive, water. And it's going to be doing the same thing as HCl. It's heterogeneous because we have H and an OH. Now, for water to add across a double bond, sulfuric acid is required. And in organic chemistry, we frequently use sulfuric acid, sometimes phosphoric acid. Those are the 2 main acids we use. For example, when we make aspirin, we're going to be using probably phosphoric acid. I need to look at it, but I've done aspirin about 70 or 80 times in the labs over the last 12, 13 years, and we use either H2SO4 or H3PO4, sulfuric or phosphoric. I like to use phosphoric. It isn't as strong as H2SO4, but anyway. All right, so let's add water now. So here we have double bond. I'm writing water like this. Instead of H2O, I'm writing it H-OH. Frequently in organic chemistry, we write water this way, because water is both an acid and a base. Okay, so we're going to add it just like we did with the HCl. Only it's H-OH now. And you have to make sure you put in the H2SO4 as the catalyst. So what we're going to end up doing is it's the same thing as before. It's going to add 2 ways. Hence, we have a mixture. And randomly, it's gonna hit that 50% of the time. But what's gonna happen is because one is gonna be more stable than the other, we'll get a mixture that predominantly one or the other. And this is exactly what we just did. So let's look at an example. Let's do propene. So the H dash OH is going to add once randomly, and then randomly it's going to act the opposite arrangement. So this ends up looking just like we added it HCl. Okay, which one's more stable, left or right?
The left.
Exactly the same reasons as before. Yeah. The left one is more symmetrical. The left one has more terminal hydrogens.
And then to name those, the mixed ones, it would be 3 propane and 2 propane, 2 propane pertaining to the one on the right.
No,
No.
this is an alcohol.
Okay.
So the next chapter is on alcohols. So you haven't learned how to name these yet. An alcohol
Okay.
has an OL as the functional group name. So this
Right.
this would be 2 propanol. And this would be 1 propanol.
Okay.
And think of alcohol, when you look at the ending on alcohol is an OL. And then we circle that one. So that would be a typical reaction. We have reactants, we have conditions. If we have a mixture, we circle the one that's the most stable, and then we name reactants products. Now in a test, there are 2 kinds of ways I can ask a reaction problem. I can give you the reactants like propene. I'm going to throw in some water and some acid. What do I get? The other type problem is I give you the product and I say how to make this. Okay. So let me give you one of those. So how do I make that? There's a couple ways to make it. So we're doing this in reverse. So how do you get an alcohol? You start with an alkene. How do you get an alcohol? We start with an alkene. Okay, so what is the alkene then? So let me give you a process to go through. Most of the time, not all the time, most of the time, the backbone is maintained. So That's the backbone. So how many carbons do we have in the backbone?
4.
4. So we're going to start with a backbone of 4. Okay. Now to make an alcohol, we had water across the double bond. So the trick is, where's the double bond that we start with? It can be in one of two places.
If you're numbering it from right to left,
Yes, let's do that.
it would be between carbons 1 and 2 or 2 and 3, correct?
Perfect. Yes. Perfect. So if we had that, let's get rid of this down. We had it there, if we had it there. And either one would be fine. Now, if we start with this, we have to have conditions. If we start with this, we're going to get a mix. We're not just going to get the one on the right here. We're going to get a mix, but that's fine. That's life in organic chemistry. You always get a mixture. You have to purify it and stuff. So whenever I give you a product and I say, how do you make this? You have to kind of back up. Now, does everyone understand how we ended up with 1, 2 double bond, 2, 3 double bond? Okay, so let's jump over to okay. So I want to make an alcohol. From what do I start with to get that alcohol? The alkene. So we throw water, sulfuric acid, and then alkene, we're going to end up with alcohol. That's the beauty of using this flow chart. So if I give you the product, that's the head of the arrow, the reactants are tail of it. Now, there are other ways to make alcohols too that we haven't talked about yet. That's starting with a aldehyde or ketone, but we're not going to talk about that now. Only thing we learned so far is alkenes. So I'm going to put that off the chart. So we want an alkene. How do we get it? Should we want an alcohol? How do we get it? We can get it from one source, from an alkene. That alkene needs to be in water and a sulfuric acid catalyst. Now, does using this chart make sense? You can have this chart on your tests, by the way.
Yeah, the chart makes a lot of sense. It's really helpful.
Should we ignore like the heat or spark, like to convert from alkane to like haloalkane, or should we like just like ignore for now, or should we just like read it still and have
Well,
it in our head?
What the spark means is combustion.
Yeah.
If you want to burn an alkene, you can't just burn it. You have to have a spark. So to go from an alkene to combustion products, we need to add the spark.
Is that same for the alkane to haloalkane when it says UV or heat?
Actually, that's a good observation. Yes and no. Usually when they say UV or heat, We're not talking about a spark. They're talking about just plain old heat or a UV lamp. A spark is kind of a real, very short-lived, but very intense amount of energy.
Yeah.
So if you took an alkane and chlorine with a spark, you might produce a little bit of haloalkanes. It wouldn't be very efficient though. It would probably work though. I've never thought about throwing in that.
So the spark is kind of replacing the AB. It's not actually a compound, but like in this case, that's what it would be. Like the Cl2 is the AB for the alkane to haloalkane. So for the alkane to CO plus H2O, the AB is technically the spark, even though it's not like an A and a B bonded to each other.
No. One is an addition reaction. The other is an oxidation reduction reaction. Whenever we
Oh, okay.
whenever we burn something, it's an oxidation reduction reaction. So the spark is not a material thing, it's just energy. Where this up here is actually material, it has mass, and this would be the energy.
Okay.
Now, if you go over to Canvas files and go down to Unit 1, worksheets, I've added a lot of worksheets for practice. These are naming and reactions both. So there's 7 worksheets there. Additional practice. And these are all using line drawings as well. All the products of these reactions. See here, this is a colleague of mine up in Washington. Instead of putting it here, which we can't draw on this, above the arrow, he just said plus H2. So these are 7, 8, 9 are homogeneous additives, 10 is homogeneous, 11, 12, 13, 14 are all heterogeneous. So you're going to get a mixture on 11 through 14. But anyway,
Professor, really quick.
yeah.
For number 7, would you just put each of those hydrogen on either side of the double bonds?
Yep.
Okay, and then same with number 8 with the chlorine,
Yep.
correct?
Yep.
Okay.
And number 9, again, put the bromines on either side of the double bond because those are adding homogeneically. You're adding across the double.
Yeah, those are homogeneic because they're the same element, but hetero would mean because they're different.
Yep, exactly.
They need to be flipped.
And the 2 main hetero we have so far is water and hydrochloric acid, H2O and HCl.
Okay,
And
great. And it probably wouldn't be very different for HBr.
Correct.
HCl. Okay.
is 9 a cyclic compound, or
Yeah,
why is it a square? Okay.
it's cyclic. It's 4 carbons.
And then so will the additive always go to the place where the double bond is?
Yep.
Okay, could you go back really quick to when you were talking about where to place the double bond when we're making the reactants?
Yeah, let's go back to. Okay, was it this screen or earlier?
I think it was this one. I think I just missed, like, you were like, where would you put the double bonds? And then I like spaced out.
Okay, so think about this. There are, on number one, carbon number one here, there are 3 hydrogens, right?
Hmm.
Let's just show one of them. On number 3, there are 2 hydrogens. Let's just show one of them. So to make water, you pull off OH and an adjacent carbon hydrogen. So that's why double bond is over here. Carbon number 1, carbon number 2.
Wait, you have 3 hydrogens on the 3rd carbon or 2?
2.
Okay,
The
okay,
3,
okay.
the 3 is just numbering the carbon number 3.
Right. I think you said 3 and it threw me off. Okay, 2 and 2. And then the double bond would go there because
We need water
okay.
because we're adding water across the double bond.
So it could go there or to the 2, 3.
Yep. That's water.
Okay,
That's why we have 2 versions.
got it. You just need to make sure you have water because you formed an alcohol and your reactants have to include water and sulfuric acid.
Yep.
Okay, got it.
Let me do a cyclic one while we're on this. I wish he hadn't done the 4 carbons. They drew it as a box. Let's do that. So that's 5 carbons. So that would be 1 cyclo pentene. Okay, so the OH is going to go across this side of the double bond and this side of the double bond. So we're going to end up with so how would we name this? It would be 1 cyclo pentanol. That's an O, not an A. Now, when you're writing the O's and the A's, we're also going to have an Al functional group. That's called a aldehyde. So make sure you distinguish the O from the A, because that's an aldehyde versus an alcohol. Not the same thing. All right, how would we name the second one?
I am not sure.
Okay, well, whenever we start with cyclic compounds, wherever the functional group is attached, that's carbon number 1. So this is carbon number 1, and this is carbon number 1. So how would we name the second one?
I was gonna suggest, would it be the same?
Yep, it's exactly the same.
Okay.
And I did not mean that to be a trick problem either. So is there a mixture?
I feel like no,
I agree
because
with you.
isn't it?
Yeah.
It's just rotating.
Yeah, exactly. So it's the same molecule, so no mixture.
Okay, question though. So we have to make sure we can form H2O. Do we also have to check that we can form sulfuric acid?
Well, this won't happen without sulfuric acid, so you have to put it down.
I know, but before we placed the double bond depending on where we could form H2O. So why do we pick to form H2O and not sulfuric acid?
Sulfuric acid is acting as a catalyst. Catalyst, definitely,
Oh, catalyst is not actually part of the molecule. It's just kind of, it goes in and comes out, right?
yeah,
Yeah.
it comes out the same as what you started with, though.
Right, right.
And if
Okay.
it doesn't, it's not considered a catalyst. A
Okay, got it.
catalyst
So
has-
that's why we're
Yeah.
focusing on H2O.
Yeah.
Okay, got it.
Catalyst is just to make it move, so if we looked at this, there's a hydrogen there, there's a hydrogen there, that's where the water, that's where we get water. The double bond, same over here. So if I started on the right, I wanted you to know how to make the one on the left, you have to look at how do I get the water out of this? And it has to be on an adjacent carbon also. Because there are hydrogens here as well, but it has to be on an adjacent carbon. Okay. So I just wanted to point out those worksheets. Those are good worksheets, and I'm going to post the answers. I can't remember if I have the answers to those or not. I have to look. But I want you to also, I'm going to be posting problems from your book. I really like this book. I've never used this book before. On 429, there are questions regarding the reactions. And those are the ones I'm going to have you do. And the problems are the even or odd answers in the book. Okay, it looks like there is. Boy, they're all over the place. They aren't in one thing. Mostly look like even. It varies though. Anyway, so some of the answers will be in the back of the book. Not all of them. But anyway, I'm going to be assigning some problems from 429 and 430. Okay, so let's get in. Are there any more questions about reactions? Now, I can tell you right now that reactions are, remember, every test has got three things in it: naming, intermolecular forces, and reactions. And the reactions are what most students consider the harder part of this class. Just FYI. Now, this is your first exposure really to reactions. And you can see all them, different ways you can be writing them. You've got conditions, you've got starting materials, you've got ending materials, you have mixtures, which is more stable in the mixture. You also have naming. So this is where the meat of this class is, the reaction stuff. And most people find it the most interesting as well. And this is the dilemma of an organic synthesizing chemist or a biochemist making a drug or something like that. They say, how do you get to this? What is the starting materials? What is the precursor to get to this product? Well, if we have a product and we under these conditions, we have reactants under certain conditions, what do we end up making? Now we're going to be synthesizing aspirin in this class, as I said before. So what are you going to start with? Now you haven't had acids and esters yet, so you can't answer that question. But my point is that that's what makes organic chemistry interesting and sometimes challenging as well. Notice we haven't talked a lot about numbers. We talked about numbers in terms of numbering the backbone, about as numeric as we get. Nothing about moles or anything like that. All right, any last minute questions before we go on with, there's another class of molecule in this chapter as well. That's called aromatic compounds. Okay, so let's. Okay, so aromatic compounds also contain double bonds. Only the thing about aromatic compounds is they usually contain a benzene ring or one of its structural relatives. Okay, and what they mean by that is fused benzene ring. In other words, we can have something like that. In other words, a double one, a triple one, etc. Okay, now the thing about aromatic compounds is they're usually, no, not usually, they are a six-membered carbon ring. So
The aliphatic is an alkene considered an aliphatic compound? Why are they bringing in aliphatic?
okay, because it doesn't contain any benzene.
Mm-hmm.
If it doesn't contain any benzene rings, it's aliphatic. If it does contain a benzene ring, it's aromatic.
And aliphatic are characterized because they have double bonds.
Aliphatic can have double bonds. Oops, let me say that, no, benzene.
Have we talked about aliphatic, or is this a new one too?
Okay, all we're doing is we're classifying everything we've studied to this point, aliphatic.
Mm-hmm.
Everything to
Okay.
everything to this point has had no benzene in it.
So alkenes, alkanes, they're aliphatic.
Yes, but we can
Okay.
put a benzene in there on top of an aliphatic compound, which then makes it an aromatic compound.
Got it. Okay.
So anything with benzene in it, boom, aromatic. Now, the term aromatic when you're cooking doesn't mean benzene. When I cook and I say it's very aromatic, that means it smells really nice or candle burning. That's totally different than aromatic compounds. They're not related at all. So in the chemistry sense, benzene is very unique when you say aromatic compounds. Okay, first of all, it's a six-membered ring. Six-membered carbon rings are very stable. When you alternate single, double, single, double, single, double, it's even more stable. So when you alternate the single, double, single, double, single, double, that's where the stability comes in. If you look at some general biochemical molecules, frequently you'll see single, double, single, double. They're not rings, they're just long strings, single, double, single, double. And there's very inherent stability and when you do that, when you alternate single, double, single, double, single, double. And it's not single, 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 double, it's alternating, single, double, single, double. When you put that in a ring, you get even more stability. Now, this exists in two structures, this one and this one. Those exist simultaneously because the double single bonds alternate at lightning speeds. So they usually represent benzene like this, with the circle in the middle. And that represents single, double, exchange. In other words, single, double, change places. I mean, we're talking about like light speed. So really, it's not a single double, it's kind of a dotted line between the two. Hence the stability. Now, remember I said earlier, double bonds were inherently unstable? By this alternating single double, we've made the double bond more stable. Because we're spreading out that instability between two carbons instead of, excuse me, we're spreading it over 3 carbons rather than 2 carbons. Hence, benzene is more stable than a, just say 1 carbon, 1 double bond in the ring, or 2 double bonds. We have 3 double bonds in the ring, in the 6-membered ring. We alternate single, double, single, double. And that's where the word resonance comes in. There's a resonating from one form to the other. Super fast.
So, what did you just say? Resonating?
Yes, resonating. Okay.
That means, okay, I'm trying to picture it. How are they moving? Are they switching places? Is the molecule as a whole like rotating?
No, what's happening is, remember we talked about in a double bond, there's a sigma electron and a pi electron. And the pi electron was the more unstable one.
Yeah.
That's the one going back and forth. So we have a
So the electrons are moving?
yes, the electrons. Oops. So in a double bond, we always have a sigma and pi electron. And this is going to be the pi electron. And the pi are the ones that are going back and forth. So the instability of the pi electrons being shared. So when we talk about resonance, we are sharing the unstable electrons, which are the pi's. And because we're sharing it, it's like having a bad relative. If the whole family helps out with the bad relative, it's easier on everyone rather than just one person. Exactly the same metaphor. That pi electron, unstable, but if we can move it around, then that pi instability is not being felt by just one carbon, being felt by many carbons. And that's where the resonance concept comes in. So we're sharing unstable electrons. Those unstable electrons are pi electrons. So if we complete this now. And so those pi electrons are kind of going back and forth between all the carbons. So there are 3 double bonds, 3 single bonds. Those 3 pi electrons are zooming back and forth between all those 6 carbons. So that 6 carbons are sharing the instability of 3 pi electrons. As opposed to that. So that pi electron over here on that single double bond is being shared much more than, it's not being shared at all. It's not being shared, hence the benzene resonance structure shares those 3 pi electrons with 6 carbon electrons, 6 carbon atoms. Okay, so bottom line is we're sharing unstable electrons. This is not shared, hence It's got the full instability of that pi electron. That's why benzene is more stable. Also, there's only one hydrogen here. So it's C6H6, not H12. If we didn't have double bonds in here, it'd be C6H12 with the double bonds, 3 of them. We have C6H6. Okay. And this is basically what this slide here is all about. So from now on, we're going to be drawing benzene like that. All right. We can replace one of the hydrogens with various things. And the way we name it is, now this is a tricky part on naming, is when we talk about benzene. This benzene can be both a branch and the main molecule. Main molecule or branch. When the benzene is the main molecule, like here, we have to use the word benzene in the name. And then the branch is that, ethyl benzene, nitrobenzene, bromo or chlorobenzene. These are official common names. Instead of saying methylbenzene, we say toluene. Instead of saying hydroxybenzene, we say phenol. Instead of aminobenzene, we say aniline. And I don't know, this is, I've never seen another name for benzoic acid, but this is the acid form. Now, phenol, we're going to be talking about that as a special alcohol when we talk about alcohols in the next chapter. Now, the tricky part is what happens when benzene is a branch. Unfortunately, it's not called benzene anymore. It's called phenol. Phenol. So this backbone here is 1, 2, 3, 4, 5, 6, 7. So it's 7 carbon backbone. So it would be 4 phenyl heptane. You'd never see it written like C6H5. You'd always see it written like this. So if you see benzene rings coming off a backbone, in this case, the backbone is cyclobutane, and the phenyl groups are coming off the same carbon, so it's going to be 1 di phenyl butane. Oops. Cyclobutane. Bottom line though, branch called a phenyl group. If it's the base, it's called benzene. And it's confusing, I know. I've been to this lots and lots and lots of classes, and they all get confused on that. So whenever the benzene is a branch, it's considered phenol.
And you're saying don't worry about the other example, it's just showing another version of like a branch.
Say again?
You're saying don't worry about the other example, like we don't need to know how to name that. It's just showing another form of the branch, or we should know how to name that.
Oh, yeah, you need to know how to name this.
Okay, why'd you cross it out?
Oh, because it's they put the formula down.
Oh, okay. Oh, it would be shown how you have it on the side.
Yeah, yeah.
Got it.
You'll never see it as C6H. I don't know why they use that example. To me, that's very confusing. This is the way you'd see it over here on the right. Okay. Yet again, there's another weirdness about benzene. When you have two branches on benzene, instead of numbering this as 1, 2 dibromo benzene, they name it ortho dibromo benzene. So there's two ways to name this guy. 1,2-dibromobenzene, which I think is very clear. Ortho is an ancient way of naming these. There's ortho, meta, para. Okay, so ortho, think of the word or. Or means small word, that means they're together. Para, think of paragliding. Paragliding is you need wings. Wings, paragliding. And the one in the middle is meta. So ortho, meta, para. Ortho is they're right together. Para, they're opposing. Meta means they're in the middle, separated by one. Okay, the other way to name this guy the meta would be 1,3 dibromo benzene. And this would be 1, 4. There we go. 1, 2, 3, 4. Both names are accessible. So if I asked you on a test, what's another name for 1,4-dibromo benzene, you'd say para dibromo benzene.
Wait, can you repeat that?
These two names are another way of naming them. So when you have two substitutions on the benzene ring that are opposing one another, that's a para naming, or 1,4.
Oh, okay. My bad. You just said that both the names you have down are both acceptable. That's what you said? Or we should
You need
only
to,
do the top name.
you need to know both,
Okay.
depending on the question. What's another way to name 1,4-dibromo benzene? Para dibromo benzene, or what's another way to name para dibromo benzene? 1,4-dibromo benzene. It's just, and depending on if you're in an organic chemistry group, they'll name it 1,4-dibromo. If you're in a biochemistry group leaning, they'll name it para. It's just biochemists like orthometa para, the chemists like 1, 2, 1, 3, 1, 4. It's and when you have more than two, typically they go by the numbering. So our class, if there's two alike, if there are two alike, there's two bromos, two chlorines, two whatever, usually we need to know the ortho, meta, para. If there are more than that, just use the numbering system. Okay, physical properties of aromatics. They're similar to alkanes and alkenes. They're non-soluble in water. They float basically. There's a lot of benzene in gasoline, for example. Because benzene is very, very stable, it tends to be very, very non-reactive. And sometimes we can substitute one of hydrogens on the benzene ring with other things, like chlorines and bromines and nitros and etc. Okay, ones to know. You need to know benzene, you need to know toluene, phenol, and aniline. Now, this is the amine chapter, so don't learn until we get to the amine chapter. Phenol is in the alcohol chapter, the next chapter. So don't worry about that till we get there. These two are in this chapter. This will be chapter 13. And you will not. The styrene is designed to make polymers or plastics, and we're talking about organic polymers, not artificial polymers. So no styrene for you. Now you'll see these benzene rings, like from a biochemical perspective, all over the place. Phenylalanine, okay? Notice that phenyl is a branch, so it's written like this, and referred to as phenyl. Riboflavin, okay? Notice here's the benzene ring, hence it's aromatic. We've got lots of other stuff tagged along with it. Still aromatic. Still aromatic. Couple things I want you to notice. Notice we have single, double, single, double, single, double. That's inherent stability for that resonance aspect, just like we talked about for benzene. That applies here as well. Okay, just defines what a vitamin is. Now, sometimes there are benzene rings can be fused with other benzene rings. These are present, for example, in creosote in your chimney when you burn a fire. You'll get a lot of these. And these are also very carcinogenic. Benzene is carcinogenic as well. You'll never see us using benzene in the lab. Very carcinogenic. Now, about back in the 70s, benzene was not considered carcinogenic because it was so stable that everyone thought it was just there, didn't do anything. The problem with benzene and naphthalene and benzopyrene, dibenzyl anthracene, all of them are also non-reactive, but they interfere with DNA transcription. Because they're so unreactive, they can lodge themselves in the spiral of DNA and mess up the replication process. That's why they're carcinogens. It's a physical process, not a chemical process. And this is why chimney sweeps, they discovered chimney sweeps were getting bladder cancer significantly more frequently than the people that didn't sweep chimneys. And they located it down to these products right in front of you, along with benzene. So when fires burn ineffectively, when you get those nice yellow flames, this is the stuff that it's making. Not good at all. By the way, when you barbecue and see those nice black specks on your barbecue that taste so good, guess what's in those? Naphthalene, benzopyrene, dibenzoanthracene as well. So eating barbecue every day for the rest of your life, you'll probably end up with bladder cancer. So it's really good. I like barbecue as much as anyone else, but having it occasionally is fine. Just don't do it every day. Our body has a nice mechanism for fixing problems in DNA replication, but it can't be done all the time. It doesn't have the capacity to do that. Occasionally it works fine. Okay, let's see. Chat lines. We had a question. Okay. Remember, your body can fix this in moderation.
I had a quick question. So, sunscreen, as far as I'm concerned, has chemical and physical filters that a lot of the times are also composed of some formulation of benzene rings, I think. But those are beneficial for us because they protect us from the UV rays. So, and they actually prevent cancer in that case.
Yeah, you're saying that UV rays can be absorbed by these compounds? Is that?
Yes, and those
Right.
are made up of some form of benzene.
Yes, that's right. That's right. Yeah, so resonance compounds can absorb UV energy very well. And what happens is because of the resonance structure, it's able to deal with the extra energy of the UV better than a non-resonance structure. Because that energy is spread out over all those unstable pi atom electrons, and it's able to spread out the energy, so it isn't as bad as with a non-resonant structure.
Okay, thank you.
So you'll find in suntan products frequently lots of benzene-related compounds. And some people say some of those sunscreens are not very good for you also for this reason.
Yeah. Like oxybenzone, for example, I think was found to be carcinogenic too, and it's not a filter in many commercial sunscreens anymore. But they replaced it with another one. So some of them are still okay, I guess, but I don't know.
So this would be a good
Too.
good poster project for you. How do sunscreens work? Good or bad, pros and cons. Okay, so we've covered chapter 13 here, covered a lot of material Monday and today. We talked about reactions, double bond reactions, the alkene reactions. We talked about aromatic compounds. And we're not doing any reactions with benzene. You can do reactions with benzene, but unless it's just a kind of a branch that really doesn't participate in any other reactions. Let me give you an example. Okay, say we had that. So that is 1, 2, 3, 4. So that's a butene. So we have a 3-phenyl. One butene. Similar, well, let's see. It's PENN. Okay, so we have an alkene. We have water, sulfuric acid. So we are going to form Since this is a heterogenic additive, we're gonna have a mix. Those are the two mixtures we're gonna get. Which do you think is more stable, left or right?
I want to say right.
The right one is got, you look at 3, 2, 3. So it has more terminal hydrogens for one, so Markovnikov's rule will come into play. Also, symmetry-wise, you know, that's kind of a squint your eyes, make everything fuzzy looking. Where when you have the OH on the very, very end, that really skews it. When what's in the middle, it's more uniform. So symmetry is a little, you know, wishy-washy, but it's a solid Markovnikov. So the right one is more stable. So we name that by doing looking at 3, phenol, 1 butyl, 3 phenol, 2 butanol. Okay, here the phenol group is just being drug along, just as if it was a methyl group. It is not really participating in the reaction at all. That was my point of doing this. And also just more review on doing reactions. So I've heard a lot from some of you and not a lot from a lot of you. So hopefully this is sinking in. Your book does a pretty good job on explaining these as well. And look for some problems being assigned on 429 and 430. Okay, that's what I wanted to cover today. Covered a lot. So I was going to end it here unless you had any other questions.
Regarding the holiday on Monday, are we making up that lab for
You're
the Monday section?
You're just going to do it the following Monday.
Okay, so then we would then be behind the Wednesday lab?
No, because the Wednesday lab, that week that you do the Monday lab, we're going to have a reaction review,
Okay,
and everyone's invited to that.
okay. And then so not next week, but the week after that, week 3. Is that when we're doing dry lab 2? Or is that the orange experiment?
No, okay, so dry lab 2 for Wednesday is going to be next week. Dry lab 2 for Monday, folks, is going to be the next week. And then after that is going to be the orange lab.
Okay.
So it's ways off.
Okay. Okay, got it. And then I think the due dates might be a little bit off then, because I know dry lab 1 was due today, at least for me, but we just had that on Monday.
Oh, I'm gonna change it as soon as we get off. I always
And
give,
then I think,
I always give you a week.
okay, and you might need to check that for dry lab 2 then, because I think that's due next
Yeah,
Wednesday for
okay.
us.
These were
Okay, cool.
these were done before, and I don't know. Oh,
Okay. Got it. Thank you, Professor.
sure. Are you do have lab today or Monday?
I'm in Monday.
Monday, okay. Yeah, so that's why you were asking about Monday. That makes sense. Okay, anything else, you guys? All right, go ahead and look at those extra problems I posted in files. That could be some good practice for you. The Wednesday review is going to be, you look at your schedule. It's going to be September 13th. So basically, no lab on September 4th. Wednesday, September 6th is dry lab number 2. That's for the Wednesday folks. 9/11 is the dry lab for the Monday folks. And then on that Wednesday of that week, it's a review. Now, test 2 covers more material than test 1. It's just I like to use less material for the first test because it's just a different way of studying. This class is more like almost like A and P, a lot of memory, and then at the same time it's an application as well. So it's kind of a nice mix of concepts. Okay. All right, so I'm going to say bye, and I'm going to go do some work on Canvas due dates. All right, you guys. Wednesday, folks, we'll see you in a little while. Take care, all. Oh, and have a good holiday for everyone else. The weather looks like it's going to cooperate.